So, before leaving the class yesterday, I told you that for every problem, we need not really try to get the distribution of velocity field or the shear stress on the wall, etc. Or for every problem, these details may not be required. On the other hand, there are situations in which we will be given to calculate, for example, the size of a pump or the rating of a pump, which is needed in order to pump a certain rate of water at a certain rate into an overhead tank. Or for example, in metallurgical engineering problems, the task may be that I have a 150 ton ladle and there is a hole at the bottom, ladle nozzle, and if I start to drain that as a gravity induced flow, how long will the flow take or the ladle to become empty. So, to discuss this later classes of problem, what we should resort to is not elaborate momentum balance, but macroscopic mass momentum and energy balance. So, that is the topic of today's discussion, and we will, for example, as I have indicated, that if you take an overhead tank, okay, so we are trying to find out that if you have a vessel here and if you want to pump a liquid into the water tank to fill it at a certain rate. So, I give you the time, for example, I want to fill this vessel in half an hour flat time, and then you tell me that what should be the rating of the pump that will allow me to pump and achieve this particular target itself. So, this is one class of problem that can be addressed, as I will demonstrate. Similarly, as I have indicated that if you have a ladle, for example, and then the ladle contains the material, and I would like to know that what is the complete emptying time for the ladle, so that I know that when I should have the crane available, that the empty ladle can be lifted and reused at a different site for a different purpose altogether. So, complete emptying time, where we do not require specific information on the flow. What is the flow here? What is the flow here? That is none of our interest. What is the shear stress distribution at this point? What is the shear stress distribution? These are not of our concern. Mostly we want to calculate a macroscopic parameter, in this case that being the emptying time of the vessel. And similarly, for this class of problem, the parameter of interest here is the rating of the pump, that what should be the horsepower of the pump, which will allow me to pump fluid at the specified rate to accomplish this target of filling time. Now, the macroscopic discussion of macroscopic mass momentum and energy balances can be started with a framework which I am not going to derive, but I am just very sketchily mention that if you take n as a property of a system, the rate of change of n can be given in terms of between the time, okay, T n delta plus dV, and then we say n rho dV, which is the net rate of accumulation, plus the control surface, and this is going to be n rho, use vector, velocity and area. So, this is the framework based on which we can start discussing macroscopic mass momentum and energy balances. Now, where from this is given in most of the textbooks. Suppose if you consider a volume element like this, and then this is at time t, and this is at the scenario t plus delta t. The same thing I will draw here, more or less the same thing. So, you imagine that they are the same thing. So, if you have at time t is equal to 0, this is the scenario. The dotted line represents the system, and this solid line represents the control volume boundary. So, the control volume as well as the system is coinciding with each other. There is no gap actually, whatever I have shown here, they are actually overlapping with each other. And at time t plus delta t, when the system is moving, in that case the scenario may be something like and this. So, the system has flowed out of the control volume, and we can see there are two regions. Okay. For example, 2 represents a region where the system and the control volume the system, if you take that, therefore 2 plus 3, and if you consider this to be the original case. So, in this particular case, the system, if you sum up the second part as well as the third part, in that case that is going to be equal to the original system or the original control volume itself. So, this is the scenario at t plus delta t, and if you now do the balancing of a property, that the change in the property is going to be the net rate of accumulation in the control volume plus the net efflux that you see it has flown out of the control volume. So, there is a net flow out. Similarly, there is a flow into the control volume also through the control surfaces also into the control volume. So, the net rate of change of n, in which n represents an extensive property. What that extensive property means, therefore, n could be my momentum, for example. It is an extensive property. You can divide momentum, so you can get a per unit mass, or n could be energy. More specifically, n could be enthalpy and so on. So, mass dependent properties basically. And what does this small n means? This small n means n divided by the mass. So, it is the n per unit mass is the small n. So, therefore, if n represents momentum, in that I will say that the n small n will represent the velocity in the system. So, if on the other hand, if you have energy here, so the n will represent the specific energy or energy per unit mass and so on and so forth. So, this can be arrived at, as I said, if you take a control volume at a system at time t is equal to 0, take a picture and then perform a material balance, then you will arrive at this particular expression where the first term represents the net rate of accumulation in the system of n small n in the system, and the second part essentially represents the net efflux through the control surfaces. Now, it is understood that for all steady state problem, and we are going to deal in this particular case mostly steady and in viscid flow. I will explain that what the terminology in viscid essentially implies. So, steady state flow means there is going to be not the net rate of accumulation within the system is going to be within the control volume is going to be 0. As you have seen d rho, this term we have set when we are writing momentum conservation equation. We said that nothing changes with respect to time, and hence we would say that this term would be even for a compressible flow. If the flow is steady, in that case this term appearing in the continuity equation, or this term appearing in the momentum conservation equation, for example, or x momentum conservation equation, will all be is equal to 0 for a steady state problem. There is no net accumulation in the system per se. So, therefore, for steady state scenario, this term will vanish out, and therefore, the net rate of change of capital N in the system, this left hand side is we want to find out what is the change in the property in the system, and that could be equated for steady flow system solely in terms of the flow in and flow out through the control surfaces. Now, let us look at the overall mass continuity, derivation of overall mass continuity equation, overall mass continuity. Or mass balance, I would say. So, if n represents my mass, okay, and therefore, capital N, small n is equal to 1 mass per unit mass. So, therefore, I can say this is say capital M, that is what dm dt, and that will come out to be control surface, and this is 1 into rho, which is rho is the density, u is the vector, velocity vector, and a is the area vector. Area is characterized by a normal, so it has a direction. So, that is why it is represented in terms of. So, this is the dot product of the two vectors, if you remember, and this term will come out to be uniquely is equal to 0, because there is mass is not changing as a function of time. Now, let us see that suppose we have this is the inflow. So, therefore, we can say that that is how the flow is going on. So, this is section 1 and this is section 2. So, this is inflow and this is flow. Now, at the inflow, you can look at the flow velocity vector. Okay? If it is normal, in that case you can say that typically we have, if you expand this, this is basically going to be rho u vector dA vector evaluated at 2 plus rho u vector dA vector evaluated at 1. That is what essentially net flow out through the control volume, whatever is coming in and going out. Now, if you, for example, if you for a moment consider that the flow is normal to the surface inflow, these surfaces are the through which flow is coming in and flow is going out, they are normal to the direction of the flow, then in one case you will see that the flow is directed this way and the normal is directed this way, and that is the scenario that you are going to see at the inlet. Similarly, at the outlet you are going to see that the normal is directed this way and the velocity vector is also directed this way. So, this is the v vector and this is the v vector. So, at the outlet, therefore, the normal and the velocity vector are really directed along the same direction. So, the cosine of that angle becomes is equal to cosine 0 and that is equal to 1. On the other hand, at the inlet they are going to be oppositely directed. So, the angle, what is the dot product of two vectors, for example? You take the modulus of the two vectors and then, so modulus of vector 1 multiplied by modulus of vector 2 multiplied by cosine of the angle in between. Since I have considered normal flow, okay, so therefore, what will be this term? This term should be, you take the modulus of u, you take the modulus of A, okay, and then multiply the area between the vector u and the vector A. Okay. So, the normal, in which direction the flow, the vector, this velocity vector is making with the normal, that is what will decide the angle of the two. So, you can find out, so you can write out, this rho into magnitude of u plus area of u into the cosine of angle. In this particular case, as I have indicated, that at the inlet the velocity is directed oppositely. So, therefore, the cosine of 180 degrees minus 1. So, the inlet term, which is at 1, will appear to be, for orthogonal flows, will appear to be with a negative sign, and hence I should be able to write that the overall mass continuity equation, for example, now the scenario is this is the cross section. So, that is what I am considering, and this is the cross section at 1 and this is the cross section at 2, and I say, and as you can see here that the flow is directed normal to the inlet, flow is directed normal to the outlet. It is an outgoing flow, it is an incoming flow, and here the angle is 180 and here the angle is 0 degree. So, therefore, this term, the inlet term, this will come out to be rho into, if you say that this is my x direction. So, I would say ux is the magnitude of the velocity and A, and this is evaluated at section 1. So, this is with a negative sign and then plus rho ux A evaluated at the section 2, and that is what is going to be equal to 0. This tells us that rho u1 A1 is equal to rho u2, in which u1 into A1, so this is meters per second and this is meter square. So, this becomes meters cube per second, and this meters cube per second essentially represents the volumetric flow rate of the fluid through the cross section. And the moment to multiply volumetric flow rate with rho, it becomes mass flow rate. So, the standard notation is q dot, and then we say it is q dot 2, and then we say that this is m dot 1 is equal to m dot 2. Since the cross section is not changing, it's the cross sectional area A1 and A2 are identical. That is what it is in this particular case as shown, because the plates are considered to be parallel. So, therefore, I can say that the mass flow rate of fluid at this particular cross section and the mass flow rate through this particular cross section, they are identical as per the equation that we have shown here. And if the surface is not orthogonal, in that case you have to find out evaluate this whatever I have written here, this expression, by taking into account the angle that the velocity vector is making with the area vector, and then you will be able to write down this particular the net expression or the final expression, which I have not done here. I have done it in the case of flow orthogonal to the subject. Now, let us look at the momentum conservation. Macroscopic momentum conservation. Again, let us consider now we have the same kind of a scenario 1 and 2. So, let me raise, because this discussion is no more. So, we will do momentum conservation, but let us keep the drawing same. So, the velocity is coming in here, the velocity is going out here, and we want to find out. And this is, let this be our coordinate system. That is what is this. Now, if you look at the conservation expression that I have written here, again if you are considering steady state, so momentum is mass, and mass is capital M into velocity. It's a vector quantity. So, therefore, I will say that instead of n, capital N, I am going to write, and this velocity is to be represented as the velocity vector. I am not making any assumption that it is normally directed, assigning no direction to the velocity. The first term, because it is a steady state problem, so the net rate of accumulation of momentum in the control volume is equal to 0. So, there is no accumulation, and then we are left with only the control surface, and this is n is equal to, now the small n is equal to, as I have indicated, m into v bar divided by m, and that is equal to v bar. So, instead of small n, we write the v bar, and then we have rho u, whatever I have written, and dA. That is what is the expression. So, I will write it not u here, because yes, v into dA. And this, by definition, is equal to, I may write, summation of forces, and this force is also a vector quantity. And if we do this, then we find out that this is nothing but the same expression which I have written at 2 plus So, if you evaluate this dot product, if you remember, we will get a negative sign before the inlet. Now, this term can be represented as I have shown here with an m dot term. So, I can say that this is equal to m dot mass flow rate and to this at section 2, which is the outlet, minus m dot into 1. Using the same logic that is given there, that we have rho u1 a1 is equal to rho u2 a2. So, u1 a1 is equal to the volumetric flow rate, and then that multiplied by the density, and that gives us this. So, we can say that, look, you can say that now we can write down that what is the fx component, for example. Then I would say that give me the x component of this velocity vector, and then I can say that it is m1. And if there is no mass accumulation in the system, then I can say that this m1 and m2 are essentially identical, which is equal to, and then I can say that this is Vx at section 2 minus Vx at section 1. That is what. So, there is a net force acting on the system. Since if you imagine that the velocity, because the cross sectional area is smaller here, larger here, so you can expect for the same mass flow rate, we will have a very large velocity coming out through there. So, as a result of which what happens is that there is going to be a net force which will be, which the system is going to be experiencing along the x direction, because Vx2 is larger than Vx1. So, we can perform a momentum balance by using the fundamental expression which I have written earlier in terms of capital N, In that framework, we can substitute everything and then find out that what is the momentum balance conservation. Okay? And then we can say that we can split down the forces along 3 different directions and write down that I could have written Fx, Fy, Fz also have I been given the y and z component of the flow. So, I need the x component of the motion at outlet, I need the x component of the motion at the inlet in order to find out that what is the force that. Now, when there is, for example, if you may have noticed that when the firefighters, they use the firefighting hose in order to spray water, because the jet flows out with a very high velocity, they have to really struggle hard in order to stay, because it is trying to pull it, and that is the force that I have indicated here. So, the direction in which the water jet is flowing, there is a tremendous amount of force acting. So, resistive force has to be applied by the firefighter in order to hold the hose at the same spot itself. It is the same momentum conservation principle at steady state can be applied in order to find out that what should be for a given configuration, given geometry of such firefighting hoses and firefighting guns, what is the forces that are being experienced, because if too large a force is experienced, in that case the person may be actually dragged by the flow which is flowing out through the exit nozzle. Now, let us do the macroscopic energy balance. Again, we can have a similar kind of a figure here that is represented. Okay. And you may have noticed that the equation that I am writing has no dependence on x, y and z, and that is why the term macroscopic indicates the position dependency has vanished. On the other hand, in Navier-Stokes equation, when you have written or we have done a momentum conservation over a small little volume element, we have found out there is an x dependence, y dependence or z dependence, okay, or r depending on the coordinate system chosen, maybe for cylindrical polar coordinate system for a 3-dimensional flow is r, theta and z dependence of the velocity components. But in this case, the mass continuity expression that I have written, mass balance equation and the momentum balance equation, they have really nothing to do with the position dependent features. Only thing is that I have written an Fx, which essentially represents the direction of the vector, okay, or the component of the vector, force vector along the x direction, but as such there is no position dependency in the expressions that I have derived. Now, in terms of energy, one can also start with the same expression and apply first law of thermodynamics, but I want to do it in a much simpler way, the derivation. So, you can imagine that when flow is taking place through this section, we have to really push the liquid in order to flow. And on the other hand, at this particular cross section, this liquid which is coming out, the liquid is pushing the liquid which is ahead of it in order to come out. On the other hand, for the liquid to get into this, we have to do some external work and push the liquid. So, here therefore, work is being done on the liquid in order to push it into the tube, and here the fluid wants to come out, and work is done by the fluid on the surrounding fluid. So, work is done on the fluid and work is done by the fluid at the outlet. The difference between these two work in thermodynamics is termed as the flow work. And the flow work per unit mass is defined as P1 minus rho minus P2. That is the flow work. P is the pressure at this particular point, and P2 is the pressure at this particular point. That is what it is. So, this is a positive quantity. We have to pump it into the system. At this flow work, it says flow work done by the fluid between these two sections, section 1 and section 2, which is P1 divided by rho, rho being the density of the fluid, and P2 divided by rho. And this I am considering again, as I have indicated, under steady state and in viscid flow. Basically, as the fluid will be flowing, there is going to be resistance at the wall. because of the no slip boundary conditions. The fluid is stationary wall, so the stationary wall will try to retard the fluid. But the moment I say, and that retardation is because of the property which is viscosity, okay? And therefore, the moment I said viscosity is 0 or in viscid flow, so all the second order term from the Navier-Stokes equation really vanishes. So, in viscid flow basically means that there are no frictional losses in the system, okay? Because the shear stress is equal to mu into velocity gradient or negative of mu into velocity gradient. If mu is equal to 0, there is no wall shear stress. So, therefore, in the beginning, if you assume that the flow is unsteady, the flow is in viscid, then it can be said that the flow work per unit mass or the specific flow work which is represented by this equation will be equal to change in the kinetic energy of the fluid per unit mass and the change in the potential energy of the system between in which I can say that this may be taken as Z1 and this may be taken as Z2, and therefore, we may have an arbitrary datum here with respect to which these Z1 and Z2 are going to be measured. This expression, which is basically work is nothing but energy dimensionally. So, this is the kinetic energy, this is the potential energy, and this energy balance expression in the literature is termed as the Bernoulli's equation. Or we can say that if we rearrange the term, for example, then we can say that P2 by rho plus V2 square by 2 plus Z2 GZ2 is equal to P1 by rho plus V1 square by 2 plus GZ1. Alternatively, this equation can also be expressed as rho g plus V2 square by 2 g plus Z1 Z2 is equal to P1 by rho g plus V2 square, sorry, V1 square by 2g plus Z1. One and the same equation. In this case, everything is energy per unit mass. Okay? So, this term, for example, kinetic energy is mv square by 2, but the m does not appear here, which essentially means it is mv square by 2 divided by m. So, it is a kind of energy per unit mass. So, therefore, this has the dimension of meter square per second square. That is the dimension of this particular term. On the other hand, this is the same equation expressed like this. What happens? This is Z2, this is Z1, which essentially means these all have the dimensions of Z's, and Z's are the linear distances. So, this Z is meter, that this is also meter, this is also meter. And we say this is the pressure head, this is the kinetic head, and this is the potential head. So, I can make the statement in word, I can say that sum total of pressure, kinetic and potential energy at this section for an inviscid flow under steady state condition is exactly equal to the sum of the pressure energy plus kinetic energy and potential energy at this particular section. Or alternatively, I can say for steady state inviscid flows, I can say that the sum of the potential, kinetic and pressure heads here must be equal to the sum of the potential, kinetic and pressure head at section 2. Now, this equation, basically it is found that if we want to use it for laminar flow, then there is a constant which needs to be put into the kinetic energy term, and we can say that we will put it here. I think it's better. In which, So, by introducing a factor beta, now this equation can be applied to laminar flow. If beta is taken to be 1, we can say this is for turbulent flow, and if beta is equal to 0.5, it is an empirical parameter, experimentally determined parameter, that this equation works, and then we can say that this is for laminar flow. In real life problem, however, what happens is, basically at this point there may be a pump which may be pumping the fluid. Okay? So, work will be done on the fluid at this particular point. Similarly, there may be some heat which may be input at this particular section, and there may be in reality loss due to frictional forces at this particular one. So, if you express these 3 parameters in terms of their per unit mass entity and write down that small w represents the work done on the fluid by an external work done by a pump, etc., it is per unit mass. If we say that q represents the heat input to the system at section 1, okay, per unit mass, and if frictional losses represents this, then we can say that this equation, whatever I have written here, can be modified to write down that in which these are also energy term, but per unit mass, frictional energy per unit mass, heat energy per unit mass. So, we are supplying work into the system, we are supplying heat into the system, but the system itself is, or the fluid as it is flowing, is dissipating, because of the frictional losses. So, it is subtracted from this expression, and then we can remove this, because now we have acknowledged viscous, or the frictional forces, loss of energy due to the friction, wall friction, through the EF term, this particular term. So, we say that we can release these restrictions of inviscid flow, and we can say that this is now going to be applicable more or less for real life scenario, and this expression is called the engineering Bernoulli's equation. Now, let us look at one application here. Suppose I have a simple example I will first start with, draining of a ladle into a tun dish. All of you know that tun dish are used in continuous casting processes in metallurgy very frequently. It is a buffer vessel, on top of it the ladle stays, and the tun dish typically maintains a constant flow rate into the mold. There may be 1 or 2 molds, or maybe many. So, there is a ladle sitting above the tun dish. From the ladle, molten metal is fed into the tun dish, and from the tun dish, molten metal enters the continuous casting mold. That is the scenario basically. So, this is the mold basically. These are the molds. So, you have M1 and this is mold 2, this is tun dish and this is ladle. Basically, what happens is, you can expect that because these flows are all gravity driven flows, there is no pump, nothing like that, okay? No external work is being done. So, the moment I open this hole or the aperture, molten metal starts to flow in, and the molten metal. These are driven by the liquid head. You can imagine, and we will show that, when the head will decrease, then what happens? The velocity is going to be also decreasing. For higher head, the velocity or the flow rate is going to be larger, and for smaller heads, the velocity or the flow rate is going to be. So, from the ladle, Therefore, the flow rate really changes into the tundish. Now, and the tundish, what happens is if the flow rate fluctuates, then the tundish level can go up and down because the flow rate is coming in. So, we have basically what we do, whatever is the flow rate from here, we manage the same outflow rate, and as a result of which what we do, we maintain constant depth in the tundish. Initially, we fill in the tundish, and then after some time we match the inflow rate and the outflow rate, and there are valves there, of course. Through the valve I should be able to regulate the flow, and I match, and then I get a constant bath depth. If the rate of inflow is equal to the sum of the rate of outflows through the two molds, I can say that the level will be constant, and that is the period, steady state period of operating of the tundish. Now, if you consider this, and you consider that this surface is surface 1 and this is the outlet which is surface 2, and you apply the Bernoulli's equation here, okay? And then you can say that look, the discharge here is also under atmospheric atmosphere, the pressure here is atmospheric pressure, the pressure here, if you consider that this nozzle molten metal, it is an open air, then the way I have drawn it, it is an open air tubing. Otherwise, there is a submerged entry nozzle, and my discussion that I am presenting will not be valid if I consider a submerged nozzle, entry nozzle. So, let us say that the molten metal stream comes out and enters the mold, an idealized scenario. So, at this particular section, the stream is exposed to the environment. At this, the surface is also exposed. So, at section 1 and section 2, I will say that P1 is equal to P2. Now, because this interface is constant, I have matched the inflow and the outflow rates. So, therefore, the section 1 is constant, it is not moving with any velocity. So, therefore, I would say the velocity of the fluid at section 1 is actually equal to 0. And there is a height difference here, that height is small h, which represents the depth of the liquid in the tundish. So, if we now simplify this, and because most of the metals processing unit flows, we will see that they are basically turbulent flows. So, we will drop this parameter beta, okay, and we can say that look, there is no heat input to the system, this is 0, there is not heat output to the system, but there is a finite frictional losses at the wall, but let us for the time being make a simplification that there is not frictional losses in the whole system, because the depth is really not that much. So, therefore, we can say that the equation under this condition will boil down to V2 square by 2 is equal to Z1 minus Z2, and that is equal to, or I can say V2 is equal to square root of. So, that is what I was making, that the velocity through the orifice, it indicates it is directly dependent on the square root of the, it is a head driven, whatever is the position of the interface, that will dictate for a given diameter. And the volumetric flow rate is what? The volumetric flow rate is going to be the velocity multiplied by the cross sectional area, as I had indicated here. So, the moment I say that look, I will multiply it by A2, and then I get multiplied by A2, and this becomes my volumetric flow rate. And if I take the density of steel, I can get the mass flow rate. In nozzles, for example, most of the time, so therefore, the volumetric flow rate in this particular case, when under steady state condition, if the bath is changing, in that case I cannot apply really this particular formulation, because at instantaneous value I can find out when the bath is this much, depth is this much, then this applies. When the bath is depth is this much, then I will have a different h value here. So, the velocity is going to be a function. I can assume piecewise steady state, feature of the flow, and then at various instants when the bath depth is this, what is the velocity, when the bath depth is this, what is the velocity, when the bath depth is this. Assuming momentarily steady state scenario exists, then I should be able to find out that what are the velocities. But in true sense of the term, in an unsteady state flow, when the bath is going to be descending continuously, we will not be able to apply the Bernoulli's equation. Now, If you look at this parameter, so what I have written, the flow rate is equal to A2 and this is equal to square root of 2GH. Area multiplied by, and this, if it is the diameter of the nozzle is this, then this is equal to this. Actual flow requires the correcting factors, and that says Q actual. This is, we will say, Q theoretical, and we will say Q actual, that will require in industrial flows a parameter which we call as, in which CD represents the discharge coefficient. Discharge. The moment I say it is coefficient, so therefore it is understood that its value is going to be varying between 0 and 1. Now, the physical significance of this is that when we have nozzles, for example, or orifices through which fluid flows, so suppose we can have various kinds of, this is one kind of a. So actually when the flow really takes place, because of these sharp corners, the flow really occurs like this. That is the way. So the available cross-sectional area actually is not, the fluid does not see the total cross-sectional area which is available, okay? And as a result of which you can find that the discharge coefficient is going to be much lesser than unity for such sharp nozzles or sharp orifices. On the other hand, if you see that the nozzle geometry is like this, in that case you will find that the flow is occupied, so the entire, so this is the very smooth contour, a nozzle which has been fabricated taking into account the streamline of the fluid motion. In this kind of a geometry, this is the geometry 1 and the geometry 2, we can expect that the area is smaller, but this is more or less the same area through which the fluid flow is occurring, the total area is available. So in this case the discharge coefficient will be very close to unity, okay? And typical values of discharge coefficient for such nozzles are 0.95 or 0.98. On the other hand, the discharge coefficient here can be smaller than unity and much smaller than unity, and that value could be 0.8 to about 0.85. So you can determine the discharge coefficient by taking the ratio of the two. That means you just apply a measuring device here, okay, and then you can monitor if you know the density, or you can collect in a container the whatever is the fluid which is flowing out, measure it by noting the time, you can find out the flow rate. So you can experimentally determine the flow rate, and you can theoretically always calculate the flow rate, and then you should be able to very easily determine that what is the discharge coefficient of the nozzle that we are considering. So now, given this background, we have more or less covered the essentials of the flow dynamics that we will really require to use in the context of solving metallurgical problems. And now I want to talk about the industrial flows, and in such context I just want to introduce one term before I leave you for today. In the Bernoulli's equation, if you remember, I think it is done just a couple of minutes back, I have introduced the parameter beta in the kinetic energy term, and I said that beta assumes a value of 0.5 for laminar flow and beta is equal to 1 for turbulent flow. The way initially I wrote the Bernoulli's equation, I said it is valid for turbulent flow. On the other hand, by introducing the parameter beta is equal to 0.5 in the expression of the kinetic energy, I said now the equation can be made applicable to laminar flow. Now, these two terminologies needs to be discussed extensively. One point I want to make here, that I have used so many discriminating criteria in deriving the fully developed flow equations or writing the Navier-Stokes equation in compressible flow. I have written the Navier-Stokes equation when I had 4 different forces, it was an unsteady state flow and so on and so forth. I never ever made that made that statement that my equations that I am writing are valid for laminar flow or they are valid for turbulent flow. I made that no distinction, which essentially means that the Navier-Stokes equation that I have written, okay, the 3 equations of motion and the mass continuity equation, they are valid even for turbulent flow. Now, both turbulent as well as laminar flow. Now, I want to distinguish, I want to now talk about laminar and turbulent flows, and I want to also tell you the practical difficulties in applying the exact form of the Navier-Stokes equation to turbulent flows. Now, laminar flows, for example, I have shown that we can simplify it under various categories. Okay? One important aspect was that we can have a steady laminar flow and steady turbulent flow. Steady laminar flow. On the other hand, turbulent flows, okay, are basically time dependent flows. So, the time dependent part really remains or characteristically is a feature of the turbulent flow. So, the flow may be steady, but even there may be subtle variations in the flow as a function of time. For example, to illustrate this point, if I say that if I measure the velocity as a function of time at a particular location in the system, and I say that it is a steady laminar flow, in that case my response will be constant. So, this is steady laminar flow. On the other hand, if I say that I want to talk, I want to represent the steady turbulent flow also in the same way, we will get something like a fluctuation, high frequency fluctuation, if the flow is steady. That is the kind of signal that the probe is going to give me once it is focused into a region where the flow. Nonetheless, this can be split into, let me use a different, and I can say that this is the mean component of the flow. So, there is a steady feature, the fluctuations are there, okay? And these fluctuations really in turbulent flow occurs because of the eddying motions, which are highly stochastic in nature or time dependent in nature. So, therefore, when you deal turbulent flows, basically at a very fundamental level, we have to really do the unsteady part, simulation part also. We cannot really make that assumption that the flows are going to be, steady state or steady turbulent flows, and then from that point onwards we start our discussion. But for engineering applications, there are several ways of dealing with the complex. It's a very complex kind of a flows, and we have full-fledged courses in various departments on turbulent flows. And this turbulent flows, basically one distinction between the two is that we use the Reynolds number criteria, okay? Because the Reynolds number, which is viscosity, inertial to the viscous forces. In laminar flows, the viscous forces are very important. That is one of the dominant mechanism of momentum transfer. On the other hand, if we go to the turbulent flows, we find that these are highly inertial dominated forces, okay? And there the eddying motion along with the inertial, the eddying motions are the dominant diffusion of the eddies, okay? Rather than the molecular diffusion of momentum are important mechanisms. So, in turbulent flows, inertial forces are very high, and the turbulent diffusion component is also very, very high, but the laminar diffusion component of the momentum is very, very small. As a result of which, if this term is small, the Reynolds number will come out to be very, very large. So, one characteristics of turbulent flow is that it will be exhibited with a very large Reynolds number. Yesterday, I, for example, discussed that creeping flow around a sphere, and I said that in that particular context that the Reynolds number is of the order of 0.1 or less, which essentially means that the velocity is less than a millimeter per second. That is what I have shown. So, very slow velocity where the viscous forces really predominates. The Reynolds number 1 means we have inertial and the viscous forces, molecular viscous forces or dynamic viscous forces are identical. If Reynolds number is less than 1, viscous forces predominate. If Reynolds number is greater than 1, inertial forces predominate. And in turbulent flows, what we are talking, industrial turbulent flows, for example, we can say we are talking about Reynolds number of the order of 10 to the power 5. For example, the tundish that I have drawn here, okay, we can have a kinematic viscosity of steel about 10 to the power minus 6. So, it is meter square per second. A characteristic velocity at the ladle outlet is of the order of 1 meter per second. The reactors are huge. So, if you even take just 1 meter as the reactor, okay, so that what you get 1 into 1 divided by 10 to the power minus 6, which gives us immediately a Reynolds number of. So, this is velocity multiplied by the characteristic length divided by the kinematic viscosity, which is 10 to the power minus 6. And this tells us that the Reynolds number is about 10 to the power 6. So, in most of the metal processing units, because of the large size and low kinematic viscosity of liquid metals, we will get a Reynolds number very, very large. And as a result of which, we are going to, in our cases, the role or the contribution of dynamic viscosity in transferring momentum is going to be negligible. So, these are all going to be turbulent flows or inertial dominated force, where the transport of momentum will be because of the inertial forces as well as the eddying motion that I am going to talk about a little bit in that. These fluctuations that you see here, which I have drawn, are basically the frequency of the eddy jumping. Okay, that's what they replace. So, eddying motions or the pockets of fluid, and there is also in turbulent flows per se, there is nothing like in terms of industrial flows, there is nothing like a one-dimensional turbulent flow. Turbulence is a multidimensional phenomena. Turbulence is an unsteady phenomena. Okay? So, therefore, many simplifications when you try to apply to engineering problems, okay, becomes extremely time consuming or intense. So, even for engineering cases, when we have we want to have solution in a reasonably small amount of time, we do make certain simplifications and then we try to arrive at a workable solution, which may not be very rigorous, but a physicist may be concerned with a extremely rigorous description of turbulence, and all the simplifications that we will make for engineering calculations may not be tenable. So, I will continue with the last lecture tomorrow, discussing further about the laminar and turbulent flows, and then tell you one single engineering approach, just for the sake of your knowledge, what people have been, or metallurgical engineering people per se, have been most frequently using to work out the implications of the Navier-Stokes equation in the context of a turbulent flow.